and the lighter mass is further away. So that's the whole idea behind a torque balance. Alright, so we can also have a torque balance with a stick that has an appreciable amount of mass, and when we do, then we have to account for it. So as we can see right now with our stick on the fulcrum, this would be out of balance. This stick would tip over to the right in the clockwise direction. And the reason for that is that we can say that all of the gravitational force acts on the center of mass of our object. So if we go to the center of the stick, we could say that the mass of the stick times g, the weight of the stick, would act downward right there. And since that's to the right of our fulcrum, then our whole stick would tip in the clockwise direction. But I could counteract that by taking some mass, m2, and placing it on the other side of my stick, and then I could make this thing balance. So if I did that, then all my forces I would have going on, I would also have an m2g right here. And of course the fulcrum is going to exert an upward normal force on the stick. And as always, normal force is going to have to equal the two weights combined so the stick doesn't accelerate up or down. But once again, for our stick to remain balanced, the clockwise torque and the counterclockwise torque have to be equal. So in this case, our counterclockwise torque is created by m2. That's going to try to push down the left-hand side, make the whole thing rotate in a counterclockwise direction. So if I call the distance from m2 to the fulcrum d2, then the counterclockwise torque is going to be m2g d2, and the clockwise torque is just going to be from the weight of the stick itself. And so if I say the center of the stick is some distance d1 from the fulcrum, then the clockwise torque is going to be mg d1. And once again, because these forces are vertical and the stick is horizontal, theta is 90 degrees, so we don't have to include the sine of theta. And once again, the g's cancel. So we get a very similar equation to what we had last time. And once again, the two masses do not have to be equal as long as the mass times the distance from the fulcrum is equal. Okay, so for the last problem we're looking at, we're going to look at a block that's kind of sitting just with its corner barely on the edge of a cliff. And we've got a person holding a rope keeping that block from falling off the cliff. So of course, if we look at the forces acting on that block, we would have weight going down exactly from the center of mass of that block. And then we have the tension exerted through the rope that the person is holding on the block. And then the other two forces would be exerted by the cliff itself. And first of all, we would have an upward normal force right there where those two corners overlap each other. So we have a normal force going straight up. And then we would also actually have friction, static friction, going to the left. Now, for this thing to be in equilibrium, first of all, the forces have to be equal. So the force to the right would have to equal the force to the left. And then, of course, also the force up would have to equal the force down. But also, because this block is not rotating, the torques have to be equal as well. And I'm going to look at the torques around the axis of rotation, which would be this corner right here. Because we don't want the block to start tipping over off the cliff counterclockwise or tipping over towards the person in the clockwise direction. So the first thing I see is that both the normal force and the force of static friction act through the axis of rotation, which means their distances are zero, which means they produce no torque. So then really, when I say that my counterclockwise torque and my clockwise torque have to be equal, what I'm really saying then is that the torque from the weight of the object has to equal the torque from the tension of the object. So, if I wanted to do the torque from the weight of the object, then what I would see is that the torque from the weight of the object is going to be the force times the distance from the axis of rotation. And since weight acts at the center of mass, then the weight is just the distance from the axis of rotation to where the weight is acting downward is going to be half the width. So that would be W over 2. And then the torque from the tension is going to be the force times the distance from which it acts. So it's going to be the tension. And let's say I'm pulling, my rope's attached exactly to the middle of the block. So then that would just be H divided by 2. Okay? And so conveniently here, I'm going to see that my 2's are going to end up canceling. And that the mass times the acceleration due to gravity times the width of the object have to equal the tension times the height of the object. And so what I find then is that if I don't want the block to tip over, my tension is going to have to equal the weight of the object times the width of the object divided by the height of the object. And if I pull harder than that, then this block would try to rotate clockwise. It would tip over to the right. And if I don't pull that hard, then this block would try to tip over counterclockwise to the left. Alright guys, we're going to look at a bunch of example problems of torque in class tomorrow. We'll spend the whole day doing examples, but I just wanted to give you guys a preview before we did, and I'll see you tomorrow.